Alright, so let's talk about another important problem we can start in graph neural networks, which is called linear prediction. And we will need to how to use this RGCN model we defined before for the linear prediction with this HI and these networks. So first of all, what is linear prediction? Linear prediction tries to infer the potential connection among the nodes. Then how can we do the linear prediction? So many of the problems we study in the real world can be defined as a linear prediction problem. For example, if we want to infer some potential connection among users who are friends and who are not, then we are inferring the connection or the links between the nodes, of the users, right? When we do the recommendation of some of the location for the user to the check-ins, we also infer the potential links between users and locations. And for many other interesting tasks we study in the online social networks, and we can also reduce them into the linear prediction problem as well. So how can we define the linear prediction? We know we are inferring the potential connection or the links between nodes or among nodes. Then how can we do this, right? And we can formulate this linear prediction as a classification problem actually. So we can label all the seen links in the training set as positive instances, and we label all the unseen edges as negative instances. So because we are starting the linear prediction with this HI and these settings, let's assume if we have one edge or one link, A, B, these are the two of the nodes, and its relationship between them is R1. If the A, B, R1 is seen in the training set, then it denotes it connects this A node with B node with A edge of the type R1. It will be a positive instance for this R1 relationship, right? If there's another pair of nodes, C, D, R1 doesn't exist in the graph, then it will be a negative instance. In other words, given an input heterogeneous information network, then we can extract some sets of positive instances and also some sets of negative instances and from the network, right? So we can represent a set of all the seen edges or links inside the graph as a positive set. And we can also extract all the pairs of nodes which doesn't exist in the graph as a negative pair. And this positive set together with the negative set will be forming a training set. We can train a model, right? And this is just for one single type of nodes, R1, right? Here, if we are starting this heterogeneous information networks, then we can extract a similar set for all the relationship types inside our graphs or inside the networks, right? So given the original graph, we can split this graph into different categories according to the types of relationships among the nodes. Now here we have R1 until Rn as the relationship types. So for each of the relationship type, we can extract the positive set as well as the negative set we defined before, right, from the input graph. So based on the positive set together with the negative set, we can further partition them into a training set, testing set, as well as the validation set, as we show here. So from the structure for each type of the relationships, R1, R until Rn, we can extract its corresponding positive set and the negative set. And based on the sets, we can further partition them into the training set, testing set, and validation set according to the sampling method we mentioned before for the splitting, right? So by aggregating all the training set, validation set, and the testing set for different types of the relation types, and we can integrate them together to define the final training set, testing set, as well as the validation set we show here. Right? Then we can have the training set, we also have a testing set, we also have some of the edges which can be serving as a validation set. Okay, then the question will be, if we have the training set already, how can we define a model? How can we learn a model? If we have a training set already, then how can we learn the model, for the prediction of the links among the nodes? So given a node pair, for example, A, B of relationship R1, then we can infer its corresponding label based on their learned embedding vectors we defined before, right? According to the previous pages, we know that given the node A and B with this RGCN model we defined before, we can learn their embedding vectors, right? And we can extract the last layer embedding vector as HA. This capital K denoting the depth of the model, the last layer, right, of the case layer, and also HB for the case layer, the last layer of the model. We can extract the embedding vectors for both A and B from the RGCN model we defined before out. Right. So we know the embedding vectors HA and HB already, by the RGCN model. Then we can fit in these embedding vectors to the functional component to classify them into a label, either positive or negative, right? Positive denoting these two nodes can be connected to each other. Negative denotes they are not connected to each other, right? In other words, we are inferring the potential connection among them, and we can denote this connection between them as a mapping. We define one mapping, to project this HA and HB to a either positive or negative classes, right? Then the question will be, how can we define this projection, this mapping? We can define the projection, this mapping between A and B into what? Into the inner product between HA and HB. However, here we have the relationship R, right? So to further incorporate the information for the relationship R, as we show here, we also define one variable, which is the WR as a matrix, as a variable to be learned. In other words, we can define the F mapping as what? As HA transpose times WR times HB. Its result will be a scalar. Of course, we can further feed this scalar into a sigma function, for classify them into either positive or negative classes. So this is the way we can infer the potential labels between A and B as nodes based on their learning representations, HA and HB, we show here, right? So then we can have the prediction labels by the model and for this AB, this pairs for the relationship R1 as we define here. This WR should be for the relationship R as we define here, right? And for different relationships, we can have different WR as variable to be learned to infer the labels. So by comparing these kinds of prediction results versus the ground truth, we can define loss function for learning the model, right? So this is the way we can infer the labels between the node pairs inside the HIN networks, and we can infer if there exists a link connecting them or there is no actually. Okay, so this is for the HI link prediction. So many of the real-world problems can be reduced to these link prediction problems as we define here. It will be a very important problem. We start in the HI and these networks by using the extended version of the GCN model.